SAP2000 offers a powerful nonlinear static pushover analysis option, which tracks hinge formation and helps to identify the failure modes of the structure. Pushover analysis may be performed on either existing or new construction. For the simple 3D steel frame model shown, we are ready to run a linear elastic analysis, for which the results will be used to design the frame members using SAP2000's optimized design capability. The model will be subjected to dead, live, and response spectrum loads. We can now run the analysis. Once the analysis is complete, we start the design, which will select the optimum sections from the auto-select sections list. The selected sections may be displayed on the model. It is these sections that will be used for the nonlinear pushover analysis. The next step is to assign hinges to our line objects. We unlock the model, select all, and then go to the Assign Frame Hinges command. We will use the default moment hinges about the 3 axes, with hinges located at each end of the object, 0 relative distance being one end and 1 being the other. We can verify the hinge properties generated by going to the Define Hinge Properties command. Again, we previously selected the default hinge properties, but the user should always verify that the calculated behavior is appropriate for their model. Next, we will define the pushover analysis case. Before we do that, however, we need to set the deadload case to nonlinear, so that the program can use this case as the starting point for the pushover. We will call the new pushover case push, which will continue from the deadload case. The load will be applied as an acceleration in the UX direction with a scale factor of -1. We will use displacement control and will push to a displacement of 12 inches at the top level. We will also save the analysis at multiple states. We can now run the analysis. We will shut off the response spectrum case as this was needed only when doing the linear analysis for member sizing. Once the analysis is complete, we can display the deformed shape for the pushover analysis case. We can move through the various steps and see what hinges are forming and where they are on the force deformation curve, such as immediate occupancy, life safety, or collapse prevention, as indicated by the color of the hinge. Next, we plot the pushover curve. First, for the base shear versus displacement. Notice how the base shear drops off as the hinges form and reach different states. We can also plot the capacity spectrum, with the capacity curve in green and the demand curve shown in yellow. The demand curve plotted here is for seismic coefficients of 0.4. However, we can easily vary these coefficients to see how the demand curve slides out on the capacity curve without having to do another analysis. The point where the two curves intersect is called the performance point, and it is this point that represents the global behavior of the structure. Even when the structure looks to have adequate capacity from a global standpoint, it is always advisable to check that local collapses are not occurring, which we will now do. Note that for this demand curve, the performance point has a period of 0.752 seconds. When we look at the capacity demand table, a period of 0.752 seconds occurs at nearly the second step. When we display the deformed shape for the second step, we see that only one hinge is beyond the life safety level, and because it is a beam hinge, there will probably be no collapse locally for this level of earthquake. This concludes this tutorial.